I was a little bit. Students came to my office today, and we're talking about math jokes. So every time I look up math jokes, I have to put something in here. This says, if you can't read it, see this is 1/2 and 1/2. Hey, let's make one whole. It's even funnier when I have to explain it, right? This one I won't have. This is great. Your plan has just been foiled. Now that I like that. Come on now. Come on. We just went over foiling. That's solid. I'm going to take a win for that.
I think you sent me a math meme too. That also made me like go.
Oh, I sent you a mean teacher meme, I think, yeah. Right? Like with like a teacher who looks all like.
Like I only see things important in days that have been quiet. I'm so sorry. I know.
Oh man, that's fun stuff.
Like the only thing I remember from high school math is literally this section.
Just FOIL, and that's it.
This entire section. Because I liked polynomials. I like them. It's the only like math thing that I like to get into, so you do it really fast.
Right? Yeah, polynomials are. They're kind of fun.
Years.
Okay, so I forgot my calculator today, so I might be relying on you guys for some calculations. So let's go ahead and start up. Chapter 4.7. This is going to be all about how to deal with multivariate stuff. And so you can see in our example here, we've got some terms with both x's and y's in them. So we'll show you how to deal with that in this section. And then the next section, we're going to talk about dividing polynomials. Super fun. So the first example in this section is just an evaluate example. You should start to be getting familiar with evaluation problems by now. Remember, we just call these plug and play problems. So you plug those values in and then you calculate for everything. So to plug this in, all I do is rewrite everything without an x. So I have 4 plus 3 times where x used to be. I replace it with a -2, and I throw it in parentheses because it's negative. It really, just to be safe. So then I have plus x times y. X is -2. Y is 5, and that was actually a y squared. Plus 8 times x cubed, so I have -2 cubed here, and then y cubed. I have 5 cubed here. Okay, so now after I plugged everything in, this turns into just an order of operations problem. I just have to make sure that I compute all this stuff correctly, and then I'm safe. So first thing I'll do is handle all the exponents, and maybe some of the multiplications. So I have 4 plus this should turn into a -6 here, minus 6 plus a -2 times 25 plus 8 times -2 cubed is -8. 5 cubed is 125. Okay, so I have 4 minus 6. -2 times 25 is -50. Don't know what that is. I need a calculator. -8,000. Awesome. -8,000. Okay. So what do we have here? So we have 4 minus 8,056, which gives us a -8,052. I may be making some arithmetic errors today, so beware.
What?
Right? Which is totally different from any other day. I know, it's going to come as a shock to you guys. Okay, so on the next problem, we're going to evaluate again. Once again, this has 2 different variables, right? H equals 4.7, R equals 1.2, and they say evaluate the surface area of a right cylinder based on these 2 values. So once again, we just plug things in and calculate. So I have 2 pi times R, which is 1.2, times h, which is 4.7, plus 2 pi times 1.2 squared. Okay, trying to log into this stupid computer so I can have a calculator up here.
You don't have a phone?
I do, but it doesn't I don't know. I don't really know how to use it that well.
Oh.
I mean, don't you have to download an app to get a calculator? And I don't want to download an app right
You
now.
want an Android?
Yeah.
God. They're really jibbing you.
Are
My calculator's great.
Do you have
I can flip it and it's scientific.
oh, you must
When
have
when my phone's unlocked, but
you must have an iPhone then?
yeah.
Yeah, but do you have a headphone jack?
Yeah. I have the iPhone SE, the best iPhone.
iPhone
I paid
SE.
$130 for this, and I've had it for 3 years.
Nice.
3 years.
That's pretty good, actually.
Yeah.
So
It has water damage, and it still works. It's had water damage for 2.
so let's see now. So I have 2 times. I'll just replace pi with 3.14 times 1.28 times 4.7. Okay. So for this first one, I
It
have
has a pi, but
37 point.
Ew, that's a big number.
Yeah. Do you guys have an estimate for this second term for me? So I don't have to do that again.
Wait, are we doing pi as 3.14?
I entered it in as 3.14, but since this isn't a test environment, it doesn't matter. You can use either.
Because look at how long this number is.
Yeah. All right. So what's the rough value of the second term?
9.0477.
We'll stop there. Right? You got to cut it off eventually. Okay. And so now we're just going to do our big, our wavy equals sign to show that we definitely estimated this. And I don't know. I'll just estimate it to 2 digits in. How about that? This is what I get for not bringing the old calculator. So this leaves me with a 46.82. So that's roughly where we're at. As you can see, on this upcoming exam, you will want to bring a calculator because sometimes I do put weird decimal problems and stuff like this with pi on there.
Well, because I'm normally early, can you just give me a little reminder to go back to the library?
I can try.
Okay.
But as you can see, I'm not always the greatest at remembering things. The current situation.
I say that to my boyfriend all the time. Can you remind me to do this? And then it never gets done. So I like to put it out in the world.
Right?
Maybe I'll
Because maybe I'll remember.
Yeah.
Maybe it'll come back to me somehow.
Yeah, if I say it out loud.
Okay, so that's how to evaluate with multivariable. It's roughly the same as all the evaluation. You just plug it in and calculate. So now let's go to this next section, and let's talk about what a like term is with multivariables. So let's just recall that. Sorry. Before we get into that, let's talk about counting degrees. I jumped ahead. So to count the degree of a multivariable term. Not quite. You're thinking along the right lines. I know you saw 3 up here and decided 3, but not yet. So the degree of a multivariate term is the total number of variable factors inside, right? And so for this first term, 9x squared y cubed, I can write the degree, DEG, of 9x squared y cubed. There are 5 variable factors in here, so the the degree is 5. And so you count them all up. And so since this problem has asked us to identify the degree of each term, we're just going to do this for all the terms. So the second term, I have the DEG, standing for degree, the degree of negative 14x y squared z cubed. I just count up the number of variable factors. I have a single x, 2 y's, and 3 z's. That gives me a total of 6. So the degree of that second term is 6. All right, the next term, xy, I have the degree of xy, right? There's exactly 2 variable factors here, so the degree of that is 2. And just remember, with these last terms, the degree of something with just a single variable in it is just 1. And the degree of a single constant term is 0. And I think I skipped this one, the degree is 2. Okay. And so when we talk about the degree of the entire polynomial, that's the degree of the highest degree term, right? And so one of these had a degree 6, so that's the degree of this whole big ugly polynomial. And if I wanted to know what the leading term of that polynomial was, that's just the coefficient, or sorry, the leading coefficient is just the coefficient on the leading term. So that's just negative 14.
Okay. Wait, what?
Sorry, that sounded weird. Okay, so the leading coefficient is the coefficient of the leading term, right? And so the leading term is this one, the one with the highest degree. So I look at my coefficient here, which is 14. Negative 14, sorry.
So that's the degree of the polynomial.
The degree is 6. The leading coefficient is negative 14. Okay. So now finally, let's go into what it means to be a like term in multivariate land. So basically, to be a like term, it means you have to have the exact same variable factors. So if your variable factors differ by even just 1, you cannot add them together. And so I have 4 terms in this first polynomial, so I'm just going to go through and highlight all my like terms. I see that this first term has variable factors of x squared, y, and so does this third term. Those two are like. Notice though, this one that I'm highlighting right now in yellow, this one is not like the others. Right? It's kind of a little trick here. We have 2 y's here and only 1 y here, 2 x's here and only 1 x here. That small change means they're different terms though. They're not like. And then, of course, this one on the end has also a single x and 2 y's. So it's just like its yellow buddy right there. So now I add the 2 blue terms together. I have 9 minus 5. That gives me 4x squared y. And then I have 3 minus 1. That gives me plus 2xy squared. And this polynomial right here is a 3rd degree polynomial. That's the highest degree term. I guess you could really call both these terms the leading term though if you wanted to, because they're both degree 3. Okay. It just gets uglier. Really, like the secret to this is just paying really close attention to what those variable factors are and taking your time so that you don't mix anything up. So let's see now. I think first I'll just collect my a cubed terms. That seems to be a good one to lead the charge. So I have 2 of those. I have 6.
It's gotta be in order from highest, right?
Yeah, and since like I'm looking at all these and I'm thinking, well, there's a bunch here that are degree 3. Yeah, there's a bunch that are degree 3, but this is the only one with like a straight cube. It wouldn't really matter which one went first, but because I'm a weirdo, I like that straight cube to come first. I don't know why. You guys can put it any way you want, though, as long as it's degree 3 first. So now we have 6a cubed minus 11a cubed. That's going to give me a negative 5a cubed. I like to usually cross the terms out that I've already used, especially when there's this many. So next, I'm just going to go with the a times b squared terms. So I have 1, 2, I only have 2 of those. So I add those together. Negative 5ab squared plus 3ab squared. That gives me a negative 2ab squared. All right. So now I'm just going to tackle the terms with a plain ab there. I have 7ab plus 9ab. That ends up giving me plus 16ab. And the only thing I have left is just these two terms on the end. So they just drop right down. Plus b minus 1. And we're good. Yeah, the most mistakes happen on that by just kind of like rushing just a little bit too much and not recognizing that there's one small difference in the factors.
Well, I like to write it down wrong, so.
That's another common mistake. Yeah, that's I like to. I enjoy that method.
Yeah.
Okay, so let's do a little bit of addition and subtraction, and by that, I just mean subtraction, because you guys know how to add these, right? We just did it a bunch of times. Yeah, so subtraction, nothing changes from the normal polynomial subtraction. All we need to do is recognize that we have a subtraction, apply the negative sign, and then add things just like we normally would. So this is a tedious problem. I have lots of variables here. So I have 4x squared y. Right? Everything in this first polynomial just stays the same, plus x cubed y squared plus 3x squared y cubed plus 6y. And now I go about changing the sign of all the terms in this second polynomial. So I change the sign of the first one, making it negative 4x squared y. Then I change to a positive 6x cubed y squared. Then a negative x squared y squared. And then finally I change to a positive 5y. That's a lot of terms right there.
It barely fits on one.
Yeah, it's ridiculous. It's ridiculous. So now I have to go through and painstakingly figure out which of these are like terms. Maybe the first ones I'll pick out will be the ones with 3 x's and only 2 y's. So I'm just going to highlight these. Not that one. Whoops. It looks like I wrote x to the 7th here. I'm just going to make that into a 2. Right, negative 4 squared. There we go. Okay. So 3 x's and 2 y's. I see a term here. So I have 2 terms like that. I have a single one and a plus 6. So that gives me a 7 out front. I have x cubed y squared. I definitely cross out on this one so I don't lose track of what I'm doing. All right, so the next ones I'll look at is maybe the x squared y cubed terms, right? Kind of the reverse of what we just chose. Let's see now, is there only one of those?
Yeah.
Psh, that's boring. Okay. Plus 3x squared y cubed. Cross that one out. What's next?
X cubed y.
Where's that one at?
4x squared y.
Oh, okay, this one here.
Well, there's also a x cubed y cubed that I missed. But it's okay. I'm sorry.
X cubed y cubed. Where'd that one come from?
Behind the 6.
Negative x.
Yeah, it's a negative. Yeah.
Oh. Okay. Okay, so I have x squared y. I don't know. I lost what you guys are trying to tell me on that one, so I'm just going to charge ahead. Oh, were you guys pointing out this one way over here?
Yes.
Ah! Yeah, there's only one of those. Let's just add it in. So there we go. Minus x squared y squared. Okay. So now we'll consider these ones here with the plain old x squared y. And as we can see, I have a negative 4 and a 4 here, so these ones actually just cancel each other out. Those just go away. Finally, what have I got? I've got my single y terms here and here. 6 plus 5 gives me 11, so plus 11y. Yeah, and you guys can see where that could get like a little weird, and I mean, you won't get something this ugly on a test, but you will get like multivariate stuff on a test.
You'll get worse on a test.
No, it won't be like tedious like this. But something that I do, I like to mess with you by switching around the numbers just slightly, like these ones. And so like I'll have like 3 x's on one, but only 2 on the other. I do that on exams, so just read it carefully. Okay. Multiplication of multivariate polynomials. Would you guys rather use the FOIL method or the distribution method?
Foil.
Let's use the FOIL method then.
Use the distribution.
And remember, since we have 3 terms in one of these, it's not technically the FOIL method anymore. It's something a little different, but it's still the same method. It's just with extra terms. So, okay, the FOIL method says I take each term in the first polynomial and multiply it by each term in the second. Just one at a time here. So I have my first multiplication here. 3x squared times y. That gives me 3x cubed y squared. Right, and while I'm doing this, all I'm doing is adding exponents and multiplying coefficients. Okay, for my second multiplication, I have 3x squared y times 2y. That gives me plus a 6x squared y squared. Yeah. All right. For my next 2 set of multiplications, I have negative 2xy. That gets multiplied into the first term and gives me a negative 2x squared y squared. Once again, I have negative 2xy times plus 2y. That gives me negative, whoops, not 2, that should be a 4. I'll change color too. That should be a negative 4xy squared. I know this is tedious. And then finally, I have my last 2 multiplications to do. So I have 3y times xy. That gives me a plus 3xy squared. And then 3y times 2y gives me plus 6y squared. Okay, now I got to combine all this stuff. So this first term, it doesn't have any matching terms, so it drops straight down. 3x cubed y squared. Just pretend that's a y. And then I have my x squared. Whoops, I didn't mean to scribble that out. I meant to highlight that. So then I have my x squared y squared terms. So I have 2 of those. 6 minus 2 is 4, so I have plus 4x squared y squared. Then I have my x y squared terms. Negative 4 plus 3 gives me a negative x y squared. And then finally, this little guy just drops straight down, plus 6y squared. All right, so the multivariate can definitely make it more tedious, especially when a lot of those terms don't go together. Okay. If you guys remember from your special products lecture, the special product of a plus b times a minus b is equal to a squared minus b squared. And so we just noticed before we jump into this multivariate example that this, whoops, no, this doesn't actually conform, does it? That one's FOIL. Sorry, I jumped ahead on that. That was supposed to be FOIL. Let me just erase this formula and we'll come to that later. Was not thinking. All right, so right, just because we have multiple variables doesn't mean that FOIL will not work. So right here we have FOIL. For my first multiplication, I have p times 2p. That gives me 2p squared. For my outer multiplication, the O, I get p times negative 3w, so I have negative 3wp. For the inner multiplication, I have 5w times 2p. That gives me plus 10wp. And then finally, for the last multiplication, the last two terms in each binomial, I end up with 5w times 3w, and that gives me negative 15w squared. When I combine my like terms, it's only these two middle terms that end up combining. So I have 2p squared plus 7wp minus 15w squared. Okay, squaring a binomial. We'll just write out the formula for that real quick. Remember, when you square a binomial, you end up with a result of a squared plus 2 times a times b plus b squared. And that's going to be equal to a plus b squared. So this time I didn't jump the gun. You can see we have an a plus b squared situation over here. So we can just enter everything into this formula and compute. So my a is equal to 3x, and my b is equal to 2y. So I say this is equal to a squared, and so I put my 3x in parentheses, plus 2 times a, which is 3x, times b, which is 2y, plus b squared. Whoops, almost wrote out b squared. And b squared is 2y in parentheses squared. All right, so now that I've filled in everything, I just need to simplify and I should be done here. Oops, I forgot my square out here. Okay, so this first term, 3x squared squared, becomes 9x to the fourth. The second term, 2 times 3x times 2y, that becomes 12xy. And then my final term, 2y squared, becomes plus 4y squared. Careful to make sure you put the parentheses in on here. Right, because if you don't put the parentheses in on that last term, you might be fooled into thinking you have 2y squared and that you don't need to square that 2. But the 2's got to be squared as well. So make sure you put it in parentheses. Oops, put my parentheses in the wrong place. Okay. Here we go. Here are a couple of difference of squares examples. And so remember, I'll write the formula in the middle here. This is the one I jumped the gun on earlier. A plus b times a minus b equals a squared minus b squared. Let me straighten out that 2. Okay, and like I was telling the class yesterday, this, out of all the special products, this is the one that I'm going to use the most in exams, in homework problems, and as you go on, like using the difference of squares and getting comfortable with it is going to save you a lot of time, lot. Okay, so for this one, I'm not exactly in a difference of squares spot. You can see there's no plus or minus in the middle, but if I just switch both of these polynomials around, I'll end up exactly where I want. So if I rewrite this first one as 5t minus 2x cubed y squared, and then rewrite this second one as 5t plus that same thing, 2x cubed y squared, then I am in a difference of squares situation. So I can just flop those around until I'm exactly where I want to be. So down here, I make sure I know that my a is equal to 5t, and that's a 5, not an s, and that my capital B is equal to the second term, 2x cubed y squared. And remember, the sign doesn't come with your B. So just because there's a negative on the 2x cubed y squared up here, that doesn't come down here. Okay, so the formula says this is equal to a squared minus b squared. My a is 5t, so I have 5t in parentheses squared minus 2x cubed y squared in parentheses squared. So now in the last step, I just do the math with this, right? And so I have 5t squared, so I need to square the 5 and the t. That gives me 25t. And then on this second example, I need to take this square and distribute it to each factor here. So I have minus 2 squared, which is 4, x cubed squared, which is x to the 6th. Remember, that one's multiplication. When we take an exponent to another exponent, we multiply them, which means I get y to the 4th here. And so this would be my final answer. Okay, so that's an example of difference of squares with some uglier numbers. And here's maybe one of the weirdest examples of difference of squares that we've seen so far. For this example, it's like the first 2 terms are the a, and the last 1 term is the b. And so I have capital A equals 2x plus 3, capital B equals 2y. Now when I multiply these out, I end up with a squared minus b squared. I know that this fits the formula, so I don't need to FOIL anything. I can just enter things in. And this gives me 2x plus 3 in parentheses squared minus 2y in parentheses squared. I'm not sure why my voice went up on that y. 2y? Eureka! Okay. So now in the first one, we're actually going to have to FOIL this thing out. So this gives us 2x plus 3 times 2x plus 3. Right, and I don't know if you made it to the end of the video yesterday, but if you didn't, trying to distribute this 2 into each of these terms is the absolute wrong thing to do, right? It's one of the most common mistakes is to say, well, this is just equal to 2x squared plus 3 squared. No, we got to write it out like this and FOIL everything, right? And so don't make the mistake. If there's a plus sign in your parentheses, you can't really distribute the square anymore. Oops, I wrote an extra square down here, I'm sorry. Okay. So now I FOIL these things out, right? So F, O, I, L, and then this one will just drop straight down. So my first multiplication is just 2x times 2x. That gives me 4x squared. My outer multiplication, my outermost terms, gives me 2x times positive 3. That's a plus 6x. My innermost multiplication, that gives me 3 times 2x, which is plus 6x again. And then my last multiplication, my last term in each binomial, 3 times 3 gives me plus 9. And then I had my negative 2y squared out here. That turns into negative 4y squared. So, let's see now. How should I even write this? This is a weird looking polynomial. I guess I'll just write the 2 highest degree terms first, even though it looks weird. So this one is 4x squared minus 4y squared plus 12x plus 9. And so that's definitely a little bit above and beyond what you guys are expected to necessarily like just recognize how to do in this class. But if you can recognize that that's possible, then you can use these formulas for more than just sort of the basic stuff that you think, right? And so like it could be all sorts of ugly stuff if you really wanted it to be. You could use a difference of squares, and I won't calculate this out on something like I don't know, x squared plus 5x plus z minus ky, something like that. And you could, and as long as you set it up right, z plus ky. You could use something as ugly as this with the difference of squares, just calling this whole first polynomial a and this whole second part b. It would be totally fine. Okay, so that's multivariate. Let's go on to polynomial division. Yay. Oops. Dividing monomials. Okay, so this stuff is going to be on the next exam. Mainly, I'll probably expect you to do, I'll expect you to know how to do all three types of division. This first type that we're going to go over, though, is the one that like pops up everywhere. In like, basically, we're dividing a monomial by another monomial, and to do that, you just simplify. That's it. All right, so if I have a monomial over another monomial, I simplify things one little bit at a time. And so the first thing I consider is my constant terms, right? 12 over negative 3. That's equal to negative 4, right? So I just punch that in. Then I have a cubed over a, right? I'll consider my a's separately. A cubed over a, to figure out what that is, I just need the quotient rule. So I use subtraction there. So I have a to the 3 minus 1 on top now. And then finally, I just consider my b's as it's almost like I'm considering these as separate fractions, but they all go together in the end. So with the b's, I use the quotient rule again. B to the 5 minus 2. Okay, so now I just do the arithmetic on my exponents, and this gives me negative 4x squared b cubed. And that's it.
Is this 4.8?
Yes.
Oh my god.
Yeah, so this is one that's going to just, you're going to use it so often because you're always going to be simplifying fractions. And that's really what we just did, was we just simplified. And that's what it means to divide two monomials. And that's kind of the more straightforward thing, right? There's no real special steps. All you need to do is just jump into it and start simplifying things. Okay, so the next type of division we go over is when we divide a polynomial by a single monomial, right? And so let me just scroll down. And so this next example that I'll show you how to do this on is, this is how it would look like. And so we'd have like x to the 4th plus 15x cubed minus 6x squared all over a single monomial. Right? And so the hallmark of this case is that there are no plus signs in the denominator, no pluses or minus down here. It's just a single monomial, and that's it. That's the only thing that allows us to do what we're about to do. So, if we can recall, how we add fractions with like denominators is just like this, right? We add their numerators and we leave the denominator. But one thing that we don't usually highlight is that this works in reverse, right? If you have a plus c over common denominator b, you can then split that up into two fractions. A over b plus c over b. And that's exactly what we're going to do with our little monomial hanging out down here. So, with this example, we have multiple terms on top and a single term on the bottom, so we break this up into three separate fractions. So, I end up with x to the fourth over 3x plus 15x cubed over 3x minus 6x squared over 3x. And see how I did that? I just reversed the addition of a bunch of fractions. That's it. Now we go through each one of these terms and simplify, and we're done. So on this first term, I have x to the fourth over x over 3x. So that's going to give me x to the 4 minus 1 over 3. On the second term right here, I have 15 over 3, so that gives me 5. And then I have x cubed over plain old x, so that's going to give me x to the 3 minus 1. Finally, on this last term, I have 6 over 3, that gives me 2. Then I have x squared over plain old x, that gives me x to the 2 minus 1. Okay, now I just need to go through and finish up on any, exponent arithmetic, and I should be done. So x to the 4 minus 1, that's x cubed over 3. 5x to the 3 minus 1, that's 5x squared. And then minus 2x is the final term. And you might be tempted to try and do something at this point, but just leave it. After you've simplified each monomial, you've completed the division. Even though it might not look simplified or anything like that, the division's complete, and that's the important part. Right? And so remember, monomial over a monomial, we're just simplifying. But if you've got a polynomial over a monomial, that's when we break things up into a bunch of different fractions. Okay, so now let's go over our third and final case. And this is probably, actually, I got one more of those to do before we get to that third and final case. So we got this big, ugly guy here. I'll give you a second to write some of this stuff down. Okay. And this technique especially is one that it probably wouldn't hurt to just take a few minutes and sort of memorize what we do with the fraction here. I'm always surprised at how many students get these ones wrong on the exam when it's really just all you got to remember is break up that fraction and it's good. And people tend to get that wrong, even though if you just remember that little bit, you get a bunch of points for it.
A bunch.
A bunch. Actually, it's not that. I break this up into two problems, so you only get 5 points for it, but it's still worth it. Still worth it.
Out of what?
Out of 5 out of 100 on the exam. It's worth it. It's half a letter grade, dude. Yeah.
I never learned any of that stuff.
That's okay.
They don't allow D's or F's.
They what?
They don't allow D's or F's.
So
their whole grading system, you have to get above 98 to get an A plus.
What happens if you get a D or an F though?
You retake the class.
Oh.
I got a C and I was like, is there any way I can make my grade better? Or I got a C plus.
Yeah.
No. You can retake the class.
Really? Whoa, that's harsh.
Yeah.
Okay, so for this one, we break it up into 3 separate fractions, right? So I end up with 10a to the 5th, b to the 4th, over negative 2a squared b. And so the sign that goes in the middle of these two fractions is going to be the sign from the numerator, right? And so it's this sign up here. So I have negative 2a cubed b squared over, and I keep the negative from the lower one too, negative 2a squared b. Finally, I have plus 6a squared b over a negative 2a squared b. So now I just need to go through and simplify all these individual fractions, and then I can call it good. So in this first fraction, I have my constants are 10 over negative 2. That gives me a negative 5. My a variables, I have a to the 5th over a squared. That gives me a to the 5 minus 2 up here. And then for my b variables, I have b to the 4th over plain old b. And that gives me b to the 4 minus 1. So that's our first term. On our second term, I just noticed real quick that we have a double negative. So I'm going to change that to a positive before we even start. Plus sign. 2 over 2 just cancels. And that leaves me with a to the 3 minus 2 times b to the 2 minus 1. Finally, on the last term, I noticed that my denominator has a little negative in it, so I'm going to bring that out front. So that makes this whole term negative. 6 over 2 is equal to 3. A squared over a squared cancels. B over b cancels. We're done with that last term. We just need to finish up on the arithmetic on our exponents, and we're done. So this leaves me with negative 5a cubed b cubed plus a b minus 3. That's it. And I just want to, that's the last example. I just want to do one more example of simplifying a monomial because I noticed there aren't many examples like this that we've gone over so far, and I like to put these on the test. So suppose we had a 2 over 10, a cubed over a to the 5th, b over, let's say, b to the 5th over b. So this one's only slightly different in that this a term has a larger exponent on the bottom than it has on the top. Right? So we treat these just a little bit differently, not much differently. Okay, 2 over 10 turns into 1/5. And instead of subtracting up to the top, we subtract up to the bottom because that's the one with the larger exponent. So I have a to the 5 minus 3 on the bottom. And then this one, the b's though, this is kind of what we're used to, right? There's a larger number on the top. So that stays up there. B to the 5 minus 1. And so that gives me 1. That gives me b to the 4th over 5a squared. Okay, so that's just, I don't know. Sometimes that throws people for a loop. Now, we finally get into the long division. So this is the third type. And to inform us of how this works, we're going to go all the way back to arithmetic, which I have to practice before I come to this particular lecture. Right? I forget how to do long division. So I'm not going to go into a whole bunch of explanation on this long division example, but you guys will see how similar it is to long division of polynomials as we go on. And if you want like a refresher on how to do long division on decimals, you should like look it up online. Like you could ask me, but I'll point you to an online resource that will explain it better than I will. So how we do this is we check the first digit slot, and I notice that 7 does not go into 3. So I say to myself, how many times does 7 go into 34?
4.
It is exactly 4 times. Now this is key. This is a very similar thing to polynomial multiplication. Now I multiply this 4 back into the 7, right? And I write my result down here, 28. I subtract that result from the line above it. Okay, so 34 minus 28, that gives me 6. And then I have a 0 drop down. Now I say, how many times does 7 go into 60? I think it's 8. Yes, it is 8. Yeah, and now, just like I did with the 4 and the 7, I need to take the 8 and multiply it back into the 7, right? And that's going to give me 58, and I subtract that. Is that not what it is?
No. 56.
Oh, darn it, 56. 56, excuse me. I thought I knew that one. That's what I get for getting overconfident in my times tables. No, that one I was like, and you know that.
Yeah.
Right? Overconfidence. Okay. So now, once again, I subtract this 56 from the line above it, which leaves me with a 4 down here, and my 0 drops straight down to give me 40. My decimal goes up top, and now I say, how many times does 7 go into 40? And I think it's 5. Then I multiply the 5 by 7 to give me 35. And as you guys can see, this process, at least with this example, just keeps on going. Right? Eventually, right, we have a 5 that drops straight down, and then I just keep this process going. Another option, and this is more like what we do in polynomial multiplication. So the other option would have been to stop way back up where we had the 48.
And then do one of those symbols, the wavy equals?
Not a wavy equals. It would be more like a...
Oh, the R thing?
Yeah, it's a remainder. Yeah, exactly, yeah.
Yeah.
Yeah, and so I say, well, we have 4 left here, right? And so I say this is equal to 48 with a remainder of 4 over 7.
Charter school said I wasn't allowed to use the remainder after 3rd grade. 4th.
Yeah, I know. Yeah, and it, you know, I never really noticed how helpful the remainder was to highlight it in this step, just until last semester. Usually I don't do remainders in that step. But yeah, just like we have a remainder in this, we're going to have one when we do the polynomials. And in like this realm where we could have just kept going and going and going with the decimals, we won't actually be able to do that with the polynomials. We'll have to stop eventually. So let's go over how to do this. So when I'm asked to divide x squared plus 5x plus 6 by x plus 3, I want to set it up like this. I have x plus 3, and then in my little division bracket, I put x squared plus 5x plus 6.
It's the 5x.
Yeah, and the way that, you know, the by could also be a little division sign, or this could be set up as a fraction. Okay, so now that I've set it up like a long division problem, I ask myself, I say, what do I need to multiply this x by to get the first term in my dividend, x squared? Well, x times x equals x squared, so I write that up there. Okay? So now that I have my first entry up here, I multiply it back into my original polynomial, just like I did with the long division example. So that gives me x squared plus 3x. And I just subtract this from the line above. When I do that, my x squares will completely go away, and then I'll have 5x minus 3x. That leaves me with 2x. And so just like I did with the zeros on the decimal example, I drop down the next thing in line here, which is a plus 6. Now I start the process over, except for the term that I'm trying to make is no longer x squared. It's my new sort of leading term down here, which is 2x. So I say, what do I need to multiply this thing over here in blue, x by?
+2.
Yeah, +2, you got it. Yeah, and make sure you put the sign along with it, right? Don't just write 2 here, right? +2.
Yeah, you gotta.
Gotta. Okay, so now, once again, I take my +2 and I multiply it back into my original binomial. And that gives me 2x plus 6. I subtract that from the line above. And here, I get 0, which means I'm done.
Thank God.
Thank goodness. So, something I just want to point out here, the relationship between these three quantities, right? And so, let me erase these arcs here. So this guy up here in green, this is your answer. And the relationship between these is that x plus 3 times x plus 2 is equal to x squared plus 5x plus 6. That's the relationship. There's one other way. Well, should I go over that yet? No, we haven't learned how to factor yet, so I'm not going to go over the other way. I don't think. Yeah. So that's it. And when I make these up for like the exam, I literally just like throw some random numbers in a couple of binomials.
So you don't know how long it's good. Is that what you're saying?
No, well, I know that it's going to work out to something nice because I create it from something nice. No, I don't just completely make up the numbers.
That
No,
would be
I
hilarious,
multiply
but-
two things together, right? And then I just choose one of these to be the divisor, and that's it. The other one's the answer.
Oh, yeah.
Yeah, and so and so you guys can always check your work on these division problems, right? If your answer multiplied by your original divisor doesn't give you this dividend, then something went wrong. Okay. Let's try another one of these.
Oh my God.
Oh, goodness. All right. So once again, we have a polynomial divided by a binomial. So I write my binomial out here, 2x minus 1, division symbol, 2x squared plus 5x minus 1. So I take a look at both my leading terms, and I say, what do I need to multiply what do I need to multiply my 2x by to get my 2x squared? Well, that's just x. Then I take my x and I multiply it back into the original divisor. Right? So x times 2x gives me 2x squared, just like I wanted. X times negative 1 gives me negative 1x. A common mistake in these problems is to forget to multiply this x into the 1. Right? A lot of times people forget and they only multiply it into the 2, and then things kind of spin out of control and they're not sure what to do next. Remember, we got to multiply it by both terms in the binomial. So now I make sure that I subtract this lower line from the line above it. The 2x squares cancel each other out. This negative x actually turns into a positive x, and so my result is 6x down here. Now the negative 1 that's still left in the polynomial drops straight down, and I start my little process over again with sort of a new leading term down here. Now I say, what do I multiply 2x by to get 6x? Well, that's just 3. So now I take that 3 and I multiply it back into my binomial. 3 times 2x is 6x. 3 times negative 1 is negative 3. Do my normal subtraction routine here. The 6x's cancel out. The double negative here makes the 3 positive, and I end up with a positive 2. Now, the indication of it's time to stop is when your new leading term, when there's no way to get your new leading term from your old leading term, right? There's no way to turn a 2x into a 2 without dividing by something, and that's not what we're doing here. So now we know that that 2 is just a remainder. So now we can say that all this stuff is equal to, equals x plus 3 plus, we don't write remainder still, we write 2 over 2x minus 1. Okay, so you put whatever numbers down here, you put it back over this goofy thing, and then you add it in. These are much more difficult to check your work with. You can still do it in the same exact way. I can take my result here and multiply it by 2x minus 1, and it will actually give me this. It's just going to be a pain. Like, you're going to have a big fraction to deal with and all that kind of stuff. So those are a little bit tougher to check. Okay, let's keep going here. And okay, the last one is a pesky example. So we got 2 more examples left to go. This one's sort of a basic one again. And this one, we got like 17 minutes. You guys want to try this one out? Yeah, you totally do. Here, I'll zoom it out. I'll zoom it out so you can see what I did on my last example. All right, so you set it up as, oops, x minus 2, x squared is 8x plus 12.
X.
Is that what it is?
That's what we put in there.
That's the solution? Oh, okay. That's the first one? Yeah, that's the first one. I was like, I think it's more than that, but...
Yeah. I don't know.
I'm pretty sure it's just x.
Yeah. I hope on the homework it doesn't change the x like an m, because I'm just gonna forget everything.
It might.
Yeah.
It likes to do that.
Rose before blue. Yeah, it was X.
It was x?
Yeah.
I should have known.
I did.
All right, so we got x for the first entry, right? And then we multiply that x back into our divisor. That gives us x squared minus 2x, and so we subtract that from the line above. The x squares will cancel, right, giving us 0 right here. This negative 2x turns into a positive because of the double negative. So we end up with negative 6x plus 12 right here. So now, I just noticed that in order to get negative 6x from plain old x, I need to multiply by a negative 6. So then I take that negative 6 and I multiply it back into the binomial. Negative 6x plus 12. When I subtract those lines, I get a 0 remainers, so that's it. So my answer
You made it a lot easier.
is x minus 6. Did I?
Yeah, I did plus 6, and I was like, oh, you got me. So then it's 24 over, it's x plus 6 plus 24 over x minus 2.
That'll do
It's like you thought you threw me for a loop. Huh?
Yeah, you gotta be real careful right here. When we subtract this line from the line above, a lot of mistakes happen here. Because a lot of times people forget this is supposed to be a double negative. And so we're actually adding 2x to negative 8x. It's kind of a weird thing. Okay. For the final example, we're going to go over certain types of weirdness that can happen here. And that weirdness happens when we don't have our normal sort of structure for our divisor. So when I set this up, I set it up with an a squared minus 1 outside. But what's different about this one is that I'm missing my degree 1 term in my dividend, right? So I go from an a cubed, which is a 3rd degree term, down to a 9a squared, which is a 2nd degree term, but there's no 1st degree term. So I have to put in a placeholder for it. I have to put plus 0a. If I don't do that, then things go all sorts of crazy.
Wait, can you go up for a second? I'm sorry. Okay.
Do you need a second? Catch up? Are you sure?
Now I'm just staring at
And also notice when I write out my my dividend here that it's in decreasing order. That pretty much has to happen for this long division thing to work. Okay, so I start this process. Start my process. I say a squared is one leading term in my divisor. A cubed is the other leading term. Right, the only thing I need to do here is multiply by a single a. Now I take that a and I multiply it back into my binomial. That gives me a cubed minus, what happened? Minus, what am I? Oh, minus 0a squared. There we go. And then minus a. There we are. Okay, so now I subtract this line from the line above it, and I get 0a cubed plus 9a squared plus a. Good. All right, and once again, go ahead and start this over. Something's a little weird here, though. Okay. So once again, I have 9a squared. I need a, let's see now, how do I turn a squared into 9a squared? Well, I have a plus 9 there. Okay, now that I had the plus 9, I multiply that one back into my original. Oops. And I have 9 times a squared, giving me 9a squared, and then 9 times negative 1, which would give me a negative 9 here, plus 0a.
Wait, where does 0a come from?
The 0a, I'm starting to think I should have maybe put a placeholder in my divisor too, so that you guys can see where that 0a is coming from. But that's kind of where I take it from, and so you want to look at it this way, you could say a squared plus 0a right here. And that's where the 0a keeps coming from.
I still don't get it.
Okay, we'll have to come back to it. Yeah, because this. Okay, so now I go ahead and subtract this line from the line above it again. The 9 a's cancel out, and I end up with a plus 9 here. I did something wrong on this example. Oh, there you go. You gotta watch me on this stuff. Minus 5.
I have no idea what you're doing, so.
This is a weird example that you guys won't get tested on.
Will it be in the book, though?
It might be in the book, yeah. Yeah.
Why? You don't write our homework every single day.
It's true. It's true.
Class.
That's true. So I end up with a 5 plus 9 plus 4. That's right. Yeah. Okay. And so now there's no way to get a out of a squared without dividing by a, right? And so it's that same rule that we came up with before. So even though you might want to keep going, like my mind keeps telling me to do up here, that I'm screwing something up, it's really, we can't keep going, right? And so the answer is a plus 9 plus a plus 4 over this junk. A squared minus 1.
Okay, I'm starting to get, I get what the 0 is now.
It's kind of like, it's just things get totally jumbled up and weird if you don't put that in there. And I tried to get away with not putting it in the divisor, but you can see it ended up stupid. So that's what I get. Okay, so we got 6 minutes left. I'll start with this next example, and then if we don't finish it up, I'll just end in a couple of minutes, just so we can set up another one of these weird ones. So you can see that we have t plus 3 as our divisor. And then in here, I'm going to write t cubed plus 0t squared plus 0t plus 27. So now I say, well, what do I need to multiply t by to get t cubed? That is just a t squared. I multiply my t squared back in to my divisor to get a t cubed plus 3t squared. And so you can see on this step, if I didn't put the 0t squared up here, I'd be trying to subtract 3t squared from 27, and that would be really weird. And so that's where these placeholders come in really handy. Right, and so now I say, okay, t cubed minus t cubed is 0. 0 minus 3t squared is minus 3t squared. The 0t drops down. And we might have to drop down to 27 too, we'll see. So now I start my process over again. Except for now, I have a new leading term. So I say, what do I need to multiply t by to get? Yeah, negative 3. Negative 3t, thank you. Almost forgot about that one. Negative 3t. Okay, so now I take my negative 3t, multiply it back in. Negative 3t times t gives me negative 3t squared. And negative 3t times positive 3, that gives me a positive 9t. Whoops, not a positive 9, negative 9. What am I crazy? Whoa, whoa. Okay. Draw my parentheses and my subtraction sign. Okay, so the 3t's cancel. It looks like a positive 9t is going to drop down here. My positive 27 also drops down. And this one I can actually enter one more in here, right? Because I can make a 9t out of a single t. I just have to multiply it by 9, right? So I put a plus 9 back here. Plus 9. And that one will probably be the last number I put up there. Yeah, so now, one more time, just to make sure, I multiplied my 9 into my t plus 3. And that gives me 9t plus 27, exactly how I wanted. We have 0 on the bottom, and we're done. All right. Thank you guys for hanging in there today. That was pretty brutal going from multivariate to division in the same lecture. I felt like there was a lot of droning going on there.
I was like, this is so easy. And I was like, oh, shit.
Yeah, so thank you very much for your patience and sticking with me on that.